the Master Atomic Clock Ensemble at the U.S. Naval Observatory in Washington, D.C., which provides the time standard for the U.S. Department of Defense. The rack-mounted units in the background are Symmetricum, formerly HP 5721 cesium beam clocks. The black units in the foreground are Symmetricum, formerly Sigma Tau, MHM 2010 hydrogen maser standards. An atomic clock is a clock device that uses an electronic transition frequency in the microwave, optical, or ultraviolet region of the electromagnetic spectrum of atoms as a frequency standard for its timekeeping element. Atomic clocks are the most accurate time and frequency standards known, and are used as primary standards for international time distribution services to control the wave frequency of television broadcasts, and in global navigation satellite systems such as GPS. The principle of operation of an atomic clock is not based on nuclear physics, but rather on atomic physics, and using the microwave signal that electrons in atoms emit when they change energy levels. Early atomic clocks were based on masers at room temperature. Currently, the most accurate atomic clocks first cool the atoms to near absolute zero temperature by slowing them with lasers and probing them in atomic fountains in a microwave-filled cavity. An example of this is the NIST F1 atomic clock, one of the U.S.'s national primary time and frequency standards. The accuracy of an atomic clock depends on two factors. The first factor is temperature of the sample atoms. Colder atoms move much more slowly, allowing longer probe times. The second factor is the frequency and intrinsic width of the electronic transition. Higher frequencies and narrow lines increase the precision. National standards agencies in most industrialized and semi-industrialized countries maintain an accuracy of 10 9 per day, approximately 1 part in 1014, and a precision set by the radio transmitter pumping the maser. These clocks collectively define a continuous and stable timescale, International Atomic Time, TI. For civil time, another time scale is disseminated, Coordinated Universal Time, UTC. UTC is derived from TI, but approximately synchronized by using leap seconds to UT1, which is based on actual rotations of the Earth with respect to the solar time. History. The idea of using atomic transitions to measure time was first suggested by Lord Kelvin in 1879. Magnetic resonance, developed in the 1930s by Isidore Ruby, became the practical method for doing this. In 1945, Ruby first publicly suggested that atomic magnetic resonance might be used as the basis of a clock. The first atomic clock was an ammonia maser device built in 1949 at the U.S. National Bureau of Standards, NBS, now NIST. It was less accurate than existing quartz clocks, but served to demonstrate the concept. The first accurate atomic clock, a cesium standard based on a certain transition of the cesium-133 atom, was built by Louis Esson in 1955 at the National Physical Laboratory in the UK. Calibration of the cesium standard atomic clock was carried out by the use of the astronomical timescale ephemeris time, ET. This led to the internationally agreed definition of the latest She-second being based on atomic time. Equality of the ET-second with the atomic clock, She-second has been verified to within 1 part in 1010. The She-second thus inherits the effect of decisions by the original designers of the ephemeris timescale, determining the length of the ET-second. May 2009 JILA's Strontium optical atomic clock is based on neutral atoms. Shining a blue laser onto ultra-cold strontium atoms in an optical trap tests how efficiently a previous burst of light from a red laser has boosted the atoms to an excited state. Only those atoms that remain in the lower energy state respond to the blue laser, causing the fluorescence seen here. Since the beginning of development in the 1950s, atomic clocks have been based on the hyperfine transitions in hydrogen-1, cesium-133, and rubidium-87. The first commercial atomic clock was the atomitron, manufactured by the National Company. More than 50 were sold between 1956 and 1960. This bulky and expensive instrument was subsequently replaced by much smaller rack-mountable devices, such as the Hewlett-Packard Model 5060 cesium frequency standard, released in 1964. In the late 1990s, four factors contributed to major advances in clocks: laser cooling and trapping of atoms, so-called -S Fabry-Perot cavities for narrow laser line widths, precision laser spectroscopy, convenient counting of optical frequencies using optical combs. Chip-scale atomic clocks, such as this one unveiled in 2004, are expected to greatly improve GPS location. In August 2004, NIST scientists demonstrated a chip-scale atomic clock. According to the researchers, the clock was believed to be 1/100th the size of any other. It requires no more than 125 MW, making it suitable for battery-driven applications. This technology became available commercially in 2011. Mechanism. Since 1967, the International System of Units (SHE) has defined the second as the duration of 919263177 cycles of radiation corresponding to the transition between two energy levels of the cesium-133 atom. This definition makes the cesium oscillator the primary standard for time and frequency measurements, called the cesium standard. Other physical quantities, e.g., the volt and the meter, rely on the definition of the second in their own definitions. The actual time reference of an atomic clock consists of an electronic oscillator operating at microwave frequency. The oscillator is arranged so that its frequency-determining components include an element that can be controlled by a feedback signal. The feedback signal keeps the oscillator tuned in resonance with the frequency of the electronic transition of cesium or rubidium. The core of the atomic clock is a tunable microwave cavity containing the gas. In a hydrogen maser clock, the gas emits microwaves, the gas mazes. On a hyperfine transition, the field in the cavity oscillates, and the cavity is tuned for maximum microwave amplitude. Alternatively, in a cesium or rubidium clock, the beam or gas absorbs microwaves, and the cavity contains an electronic amplifier to make it oscillate. For both types, the atoms in the gas are prepared in one electronic state prior to filling them into the cavity. For the second type, the number of atoms which change electronic state is detected, and the cavity is tuned for a maximum of detected state changes. Most of the complexity of the clock lies in this adjustment process. The adjustment tries to correct for unwanted side effects, such as frequencies from other electron transitions, temperature changes, and the spreading in frequencies caused by ensemble effects. Clarification needed. One way of doing this is to sweep the microwave oscillator's frequency across a narrow range to generate a modulated signal at the detector. The detector signal can then be demodulated to apply feedback to control long-term drift in the radio frequency. In this way, the quantum mechanical properties of the atomic transition frequency of the cesium can be used to tune the microwave oscillator to the same frequency, except for a small amount of experimental error. When a clock is first turned on, it takes a while for the oscillator to stabilize. In practice, the feedback and monitoring mechanism is much more complex than described above. Historical accuracy of atomic clocks from NIST. A number of other atomic clock schemes are in use for other purposes. Rubidium standard clocks are prized for their low cost, small size. Commercial standards are as small as 17 cm3, and short-term stability. They are used in many commercial, portable and aerospace applications. Hydrogen masers, often manufactured in Russia, have superior short-term stability compared to other standards, but lower long-term accuracy. Often, one standard is used to fix another. For example, some commercial applications use a rubidium standard periodically corrected by a global positioning system receiver. This achieves excellent short-term accuracy, with long-term accuracy equal to and traceable to the U.S. national time standards. The lifetime of a standard is an important practical issue. Modern rubidium standard tubes last more than 10 years and can cost as little as $50. Cesium reference tubes suitable for national standards currently last about 7 years and cost about $5,000. The long-term stability of hydrogen maser standards decreases because of changes in the cavity's properties over time. Modern clocks use magneto-optical traps to cool the atoms for improved precision. Physics package realizations. This section may be too technical for most readers to understand. Please help improve this section to make it understandable to non-experts without removing the technical details. The talk page may contain suggestions. December 2013. A number of methods exist for utilizing hyperfine atomic transitions. These methods, with their respective benefits and drawbacks, have influenced the development of commercial devices and laboratory standards. By tradition, the hardware that is used to probe the atoms is called the physics package. One of the actual Hewlett-Packard HP 5061 cesium beam atomic clock units used in the Hayfield-Keating flying clock experiment in 1971 to test relativity theory. Atomic beam standard. The atomic beam standard is a direct extension of the Stern-Gerlach atomic splitting experiment. The atoms of choice are heated in an oven to create gas, which is collimated into a beam. This beam passes through a state's electromagnetic, where atoms of the wrong state are separated out from the beam. The beam is exposed to an RF field at or near the transition. The beam then passes through a space before it is again exposed to the RF field. The RF field and a static homogeneous magnetic field from the C field coil will change the state of the atoms. After the second RF field exposure, the atomic beam passes through a second state's electromagnet B, where the atom state being selected out of the beam at the A magnet is being selected. This way, the detected amount of atoms will relate to the ability to match the atomic transition. After the second state selector, a mass spectrometer using an ionizer will detect the rate of atoms being received. Modern variants of this beam mechanism use optical pumping to transition all atoms to the same state rather than dumping half the atoms. Optical detection using scintillation can also be used. The most common isotope for beam devices is cesium-133Cs, but rubidium-87Rb and thallium-205Dl are examples of others used in early research. The frequency errors can be made very small for a beam device, or predicted, such as the magnetic field pull of the C coil, in such a way that a high degree of repeatability and stability can be achieved. This is why an atomic beam can be used as a primary standard. Atomic gas cell standard. The atomic gas cell standard builds on a confined reference isotope, often an alkali metal such as rubidium-87Rb, inside an RF cavity. The atoms are excited to a common state using optical pumping. When the applied RF field is swept over the hyperfine spectrum, the gas will absorb the pumping light, and a photodetector provides the response. The absorption peak steers the flywheel oscillator. A typical rubidium gas cell uses a rubidium-87Rb lamp heated to 108 to 110 degrees Celsius and an RF field to excite it to produce light, where the D1 and D2 lines are the significant wavelengths. An 85 Rb cell filters out the D1 line so that only the D2 line pumps the 87 Rb gas cell in the RF cavity. Among the significant frequency pulling mechanisms inherent to the gas cell are wall shift, buffer gas shift, cavity shift, and light shift. The wall shift occurs as the gas bumps into the wall of the glass container. Wall shift can be reduced by wall coating and compensation by buffer gas. The buffer gas shift comes from the reference atoms which bounce into buffer gas atoms such as neon and argon. These shifts can be both positive and negative. The cavity shift comes from the RF cavity, which can deform the resonance amplitude response. This depends upon cavity center frequency and resonator Q value. Light shift is an effect where frequency is pulled differently depending on the light intensity, which often is modulated by the temperature shift of the rubidium lamp and filter cell. There are thus many factors in which temperature and aging can shift frequency over time. and this is why a gas cell standard is unfit for a primary standard, but can become a very inexpensive, low-power, and small-size solution for a secondary standard, or where better stability compared to crystal oscillators is needed, but not the full performance of a cesium beam standard. The rubidium gas standards have seen use in telecommunication systems and portable instruments. Active Maser Standard. The active Maser standard is a development from the atomic beam standard, in which the observation time was incremented by using a bounce box. By controlling the beam intensity, spontaneous emission will provide sufficient energy to provide a continuous oscillation, which is being tapped and used as a reference for a flywheel oscillator. The active Maser is sensitive to wall shift and cavity pulling. The wall shift is mitigated by using PTFE coating or other suitable coating to reduce the effect. The cavity pulling effect can be reduced by automatic cavity tuning. In addition, the magnetic field pulls the frequency. While not being long-term stable as cesium beams, it remains one of the most stable sources available. The inherent pulling effects makes repeatability troublesome and does prohibit its use as being primary standard, but it makes an excellent secondary standard. It is used as low-noise flywheel standard for cesium beam standards. Fountain Standard. The fountain standard is a development from the beam standard, where the beam has been folded back to itself such that the first and second RF field becomes the same RF cavity. A ball of atoms is laser-cooled, which reduces blackbody temperature shifts. Phase errors between RF cavities are essentially removed. The length of the beam is longer than many beams, but the speed is also much slower such that the observation time becomes significantly longer, and hence a higher Q value is achieved in the Ramsey fringes. Cesium fountains have been implemented in many laboratories, but rubidium has even greater ability to provide stability in the fountain configuration. Ion trap standard. The ion trap standard is a set of different approaches, but their common property is that an ionized atom is confined in an electrostatic field and cooled down. The hyperfine region of the available electron is then being tracked similar to that of a gas cell standard. Ion traps have been used for numerous ions, where mercury 199 Hg+ was an early candidate. Power consumption. The section requires expansion. June 2008. The power consumption of atomic clocks varies with their size. Atomic clocks on the scale of one chip require less than 30 MW. The United States time standard atomic clocks, NIST-F1 and NIST-F2, use far greater quantities of power. Research. ESO's first atomic clock. Most research focuses on the often conflicting goals of making the clock smaller, cheaper, more accurate, and more reliable. Optical clocks. New technologies, such as femtosecond frequency combs, optical lattices, and quantum information, have enabled prototypes of next-generation atomic clocks. These clocks are based on optical rather than microwave transitions. A major obstacle to developing an optical clock is the difficulty of directly measuring optical frequencies. This problem has been solved with the development of self-reference mode-locked lasers, commonly referred to as femtosecond frequency combs. Before the demonstration of the frequency comb in 2000, terahertz techniques were needed to bridge the gap between radio and optical frequencies, and the systems for doing so were cumbersome and complicated. With the refinement of the frequency comb, these measurements have become much more accessible and numerous optical clock systems are now being developed around the world. As in the radio range, absorption spectroscopy is used to stabilize an oscillator, in this case a laser. When the optical frequency is divided down into a countable radio frequency using a femtosecond comb, the bandwidth of the phase noise is also divided by that factor. Although the bandwidth of laser phase noise is generally greater than stable microwave sources, after division it is less. The two primary systems under consideration for use in optical frequency standards are single ions isolated in an ion trap, and neutral atoms trapped in an optical lattice. These two techniques allow the atoms or ions to be highly isolated from external perturbations, thus producing an extremely stable frequency reference. Optical clocks have already achieved better stability and lower systematic uncertainty than the best microwave clocks. This puts them in a position to replace the current standard for time, the cesium fountain clock. Atomic systems under consideration include Al plus, Hg plus/2 plus, Hg senior senior plus/2 plus, N plus/3 plus, Mg Ka plus, Yb plus/2 plus/3 plus and Yb. The rare earth element ytterbium, Yb, is valued not so much for its mechanical properties, but for its complement of internal energy levels. A particular transition in Yb atoms, at a wavelength of 578 nm, currently provides one of the world's most accurate optical atomic frequency standards, said Mariana Safronova. The estimated amount of uncertainty achieved corresponds to a Yb clock uncertainty of about 1 second over the lifetime of the universe so far, 15 billion years, according to scientists at the Joint Quantum Institute, JQI, and the University of Delaware in December 2012. In 2013, optical lattice clocks, OLCs, were shown to be as good as or better than cesium fountain clocks. Two optical lattice clocks containing about 10,000 atoms of strontium-87 were able to stay in synchrony with each other at a precision of at least 1.510^16, which is as accurate as the experiment could measure. These clocks have been shown to keep pace with all three of the cesium clocks at the Paris Observatory. There are two reasons for the possibly better precision. Firstly, the frequency is measured using light, which has a much higher frequency than microwaves, and secondly, by using many atoms, any errors are averaged. Using ytterbium atoms, a new record for stability with a precision of 1.610^18 was published on the 22nd of August, 2013. At this stability, the two optical lattice clocks the NIST research team used would differ less than a tenth of a second over the age of the universe. This was 10 times better than previous experiments. The clock relies on 10,000 ytterbium atoms cooled to 10 microkelvin and trapped in an optical lattice. A laser at 578 nm excites the atoms between two of their energy levels. Having established the stability of the clocks, the researchers are studying external influences and evaluating the remaining systematic uncertainties, in the hope that they can bring the clock's accuracy down to the level of its stability. Quantum clocks. In March 2008, physicists at NIST described a quantum logic clock based on individual ions of beryllium and aluminium. This clock was compared to NIST's mercury ion clock. These were the most accurate clocks that had been constructed, with neither clock gaining nor losing time at a rate that would exceed a second in over a billion years. In February 2010, NIST physicists described a second, enhanced version of the quantum logic clock based on individual ions of magnesium and aluminium. Considered the world's most precise clock, it offers more than twice the precision of the original. Evaluated accuracy. In 2011, the NPL-CSF2 cesium fountain clock operated by the National Physical Laboratory, NPL, which serves as the United Kingdom primary time and frequency standard, was improved regarding the two largest sources of measurement uncertainties: distributed cavity phase and microwave lensing frequency shifts. As of 2011, this resulted in an evaluated frequency uncertainty reduction from 4.1 by 1016 to 2.3 by 1016, the lowest value for any primary national standard at the time. At this frequency uncertainty, the NPL-CSF2 is expected to neither gain nor lose a second in more than 138 million years. The NIST F2 cesium fountain clock, operated by the National Institute of Standards and Technology, NIST, was launched in April 2014 to serve as a new U.S. civilian time and frequency standard, along with the NIST F1 standard. NIST F2 would neither gain nor lose 1 second in about 300 million years, making it about 3 times as accurate as NIST F1, which has served as the standard since 1999. NIST F2 was designed using lessons learned from NIST F1. The key advance is that the vertical flight tube is now chilled inside a container of liquid nitrogen at 193 C, 315.4 F. The cycled cooling dramatically lowers the background radiation, and thus reduces some of the very small measurement errors that must be corrected in NIST F1. Applications. The development of atomic clocks has led to many scientific and technological advances such as a worldwide system of precise position measurement, the global positioning system, and applications in the Internet, which depend critically on frequency and time standards. Atomic clocks are installed at sites of time signal radio transmitters. They are used at some long-wave and medium-wave broadcasting stations to deliver a very precise carrier frequency. Atomic clocks are used in many scientific disciplines, such as for long baseline interferometry and radio astronomy. Global Positioning System. The Global Positioning System, GPS, provides very accurate timing and frequency signals. A GPS receiver works by measuring the relative time delay of signals from a minimum of 4, but usually more, GPS satellites, each of which has 4 onboard cesium or rubidium atomic clocks. The relative times are mathematically transformed into 3 absolute spatial coordinates and 1 absolute time coordinate. The time is accurate to within about 15 nanoseconds. However, inexpensive GPS receivers may not assign a high priority to updating the display, so the displayed time may differ perceptibly from the internal time. Precision time references that use GPS are marketed for use in computer networks, laboratories, and cellular communications networks, and do maintain accuracy to within about 50 ns. Time signal radio transmitters. A radio clock is a clock that automatically synchronizes itself by means of government radio time signals received by a radio receiver. Many retailers market radio clocks inaccurately as atomic clocks. Although the radio signals they receive originate from atomic clocks, they are not atomic clocks themselves. They are inexpensive timekeeping devices with an accuracy of about a second. Instrument-grade time receivers provide higher accuracy. Such devices incur a transit delay of approximately 1 millisecond for every 300 kilometers, 186 miles, of distance from the radio transmitter. Many governments operate transmitters for timekeeping purposes.